All right. Hello, everyone. Friday, week two. Very exciting. Um, Today's lecture is maybe going to be a little bit shorter and a little bit freehand because of uh, uh, reasons. I have to get to the airport in a few hours, so I'm doing my best here. Um, but before we get started, uh, this is once again the sort of daily reminder that the problem set is due by 11:59 p.m. tonight. I see there's already a bunch of submissions in Gradescope, um, but if you haven't submitted it yet, please make sure to do so. I also did say that I would be releasing the second problem set by today. Um, that is ready to go. I will post that right after class. Um, so be on the lookout for that as well. And yeah, like I said, that one is a little bit longer, or it's the same number of problems, but like one of the problems I think is going to take a little bit longer than the problems on problem set one. Um, so I would encourage you to start it sooner rather than later. Um, cool. Yeah, that's what I got for the problem set. Of course, there's the programming assignment. People seem to be doing pretty well on that. There's office hours. I think there's TA office hours today after class. So if you have questions, be on the lookout for that. You can attend those, or like stick around as always. I can help answer any questions. But yeah, there's office hours. Um, all right. I guess I'll start with, are there any course logistics questions that we can clear up before jumping into content? Cool. If not, let's get into it. So uh yes, okay. So the past couple of days we've talked about a lot of algorithm stuff, right? We've talked about asymptotic complexity and the master theorem and like solving recurrence relations and stuff to like get a good estimate for what the complexity of something looks like. And then we talked about dynamic programming a little bit yesterday. Um, I think that's pretty much the extent of what we're going to do with that. Um, and so I would like to move on to more data structure stuff today. Oh, yes. And as a reminder, sorry, going back to course logistics stuff, as a reminder, there's no synchronous class next week, through the entirety of next week. And so I will post recorded lectures. We're going to be talking about sorting algorithms. So I think we're going to talk about like insertion sort, heap sort, merge sort, and quick sort. Um, and so I'll post lectures for that. Uh, if not today, then probably by like Monday or Tuesday or something. So be on the lookout for that. Watch the lectures. There's not going to be any attendance polls. So just kind of watch them at your own pace. I'm going to go a little bit faster through the lectures just because there's they're not interactive, right? They're all pre-recorded necessarily. So feel free to like go over them at your own pace and feel free to like ask questions on Piazza and stuff like that. If there's anything that's unclear. Um, okay, cool. So with that out of the way, let's get started. Today I want to talk about trees. We're going to do a lot of this just on the whiteboard, and then some of this we'll maybe do with like live coding. So with that, I guess we can get started. Perfect. All right. And my standard disclaimer, I do not know how to make it so that the whiteboard cannot be vandalized. and I do not have any way of maintaining accountability if someone does vandalize it, but please do not vandalize it. Um, can everyone see the whiteboard, by the way, if I scribble here? Cool. All right. Thank you. Okay. So let's talk about trees, right? Uh, um, yeah. Okay. So for a uh, basic sort of introduction, right? We had linked lists, which have nodes with some kind of data in them, and then a pointer to the next node, right? And each linked list has one pointer to its next node. And then at some point, we've got like the end of the linked list, and this just points down to null, right? I'm going to use the ground symbol to denote null, right? So trees are kind of an extension of this, where instead of just one next pointer, we can have potentially multiple next pointers, right? Um, and so uh, you can imagine like to sort of draw a picture, right? You can imagine something like this. Right? Something like this. This is an example of a tree. Um, the thing to note, there's a couple like a couple things I want to make clear here, right? So first of all, um, later on in the semester, we'll start talking about like graph theory a little bit, and we'll talk about trees in the context of graph theory. And so the way to define trees in that sense is they're graphs where there's like a unique path from any node to any other node. And sometimes we'll see like these arrows. Sometimes we won't see arrows. Sometimes you'll just see the tree drawn as like that, right? And so in this case, there's sort of no direction to the links between these two nodes, for instance, right? Um, so later on this in the semester, we will think about trees that look like this, where there isn't necessarily a direction, there's just links between nodes. But for now, we are going to only consider these sort of directed trees, right? So trees with arrows along the edges. And I'm not going to make any of the like graph theoretic stuff precise just yet. Um, but yeah, okay. That's the idea of trees. Trees are a very useful data structure. As you might remember from our discussion of like recursive algorithms, a lot of like you can sort of like draw a tree that represents like the recursion pattern of a function, right? So each like node here represents a function call, or each node represents a function call, and then the edges represent like um, this function calls this function and this one and this one. And so like you can kind of like draw out the entire call stack, right? And then sort of looking at the depth of the tree or like looking at the longest path in the tree gives you the maximum size of that stack or whatever. Um, it turns out that there's a lot of algorithms where turning something into a tree also like really helps with the time complexity, or it's like a good way to it's a very useful data structure for like getting faster time complexities. In particular, if you think about like the number of nodes as being some sort of like input size, then the overall size of the tree, like the depth of the tree, is going to look roughly like log of n, right? And so if you can take some problem that requires n nodes or like n inputs or something like that, or like an input of size n, right? And you can turn it into a tree, or you can like somehow semantically encode it in this sort of form, such that the thing that you care about is more related to the depth than the number of nodes, then you pick up a factor of log n instead of n, and so you get like a better complexity. We'll talk about more specific examples of algorithms, in particular, like heap sort kind of relies on this property. Um, so if you've seen heap sort before, you'll kind of have some idea of what I'm talking about here, but we will talk about heaps and we'll talk about heap sort and stuff like that. Okay, so for a sort of precise definition, um, trees, just like linked lists, right, are a recursive data structure. So a tree is either, so if you think about like a linked list, right, it's either an integer or like whatever data type we're putting in the linked list, right? For now, assume it's an integer, or it's an integer together with another linked list, right? Like this is the next pointer, this is the value. And then if the next pointer is null, then we just treat it as just the value, right? So similarly for a tree, it's either some data. So it could be like an integer, it could be a pointer to something, it could be a string, right? Whatever the data that the tree is holding. Um, and then it's got instead of a single next pointer, we will keep like a list of next pointers, right? Something like this. Um, okay, those kind of vibes. We can talk about some vocab, right? So, given a tree like this, maybe I'll redraw it to give myself a little bit more space. Okay, and I'll like name these nodes. This will be A, B, C, D, E, and F. Okay. Um, so for some vocabulary to sort of talk about the relationship of these nodes between each other. This looks like a B. There we go. We call A the let me do this in a better color. Here we go. Okay. So we call A the root of the tree, right? So the root is the node that points to stuff but has nothing pointing to it. Um, we call the sort of dual of that B is a leaf, E is a leaf. So leaf is something that doesn't point to anything else. So all of its like next pointers are null, basically. Um, the relationship between A and D, for example, is we'll say like A is the parent of D. And then also we can sort of say this the other way around and say D is a child of A. Okay. So notice I say the parent. That's because every node has a unique parent. I say a child because, for example, A has three children, C has two children, B and D don't have any children, right? Um, so you can also say like a leaf node is a node without children, and the root is the unique node without a parent. Um, and maybe you want to kind of convince yourself that the root is unique in that sense, um, that there's like only one node without a parent. Yeah. Okay. Um, cool. Okay. So that's trees in general. Does that presentation of trees as a data structure make sense to people? Are there questions before we start talking about like specific types of trees or like specific semantics associated to trees? All right. I'm just assuming that works. Oh dear. uh, I believe you. All right, there we go. Okay, so let's start talking about more specific kinds of trees, right? So in general, we can talk about the arity of a tree, right? Right. So we'll say like a K array tree is one where every node has at most a children, right? Um, for example, if we look up at this tree, this would be like a three-ary tree, right? Or you could maybe say like a ternary tree, right? Because A has three children, no one else has more than three children. So um, we can sort of think of like C only has two children, so we can sort of think of that there being like an extra child here that just points to null. We can think of B as having like three children that all point to null, right? D is having three children that all point to null. And so we can kind of like take whatever the maximum number of children is and think of it that way, right? This is sort of a semantic thing. Um, there isn't any reason why we couldn't also think of it as like a four-ary tree or like a five-ary tree, if that's what we wanted for the problem, right? We could add as many like extra null nodes here as we wanted. Um, and so it's kind of it's not an intrinsic property of the tree. It's a property of like the problem that you want to solve with the tree. It's a property of like how you want to think about the tree, right? Um, so k-ary tree. In particular, a lot of time in this class will be spent thinking about binary trees. Right? And there's just a tree with a maximum arity of two, right? So, in the case of a binary tree, we can sort of explicitly write this down. We can give the children names, right? So we can say, like, I'm gonna try to handwrite code. Struct tree. We can give it a value, and then we can give it pointers. The left child and a pointer to the right child, right? And so here, instead of like an array of children, I know for a fact that if this is a binary tree, I'm just going to have two children, so I can just name them left and right. And in general, in this class, when we talk about binary trees, we are just going to refer to the children as the left child and the right child, even if there's not like a spatial component. Um, so something to keep in mind. Um, but yeah, okay, this is a binary tree. Um, the we can be more specific with binary tree, right? We can say something like complete binary tree. Actually, I think before I say complete binary tree, I want to talk about what the depth of a tree is, right? The depth, which I guess maybe we already have some intuition, right? The depth is the length of the longest path from the root to any leaf, right? So we have a root. We look at the path from the root to any particular leaf, and whatever path is the longest, the length of that is the depth of the tree, right? Maybe uh, um, maybe someone can tell me what the depth of this tree is. I'll erase all of the null pointers that I drew in to make it less atrocious to read. Three. Okay, great. I see a three. Um, do people agree that the depth is three? Yep. So, I mean, I guess there's two ways of thinking about this, right? We could start at zero and we could say that we're counting like the number of edges in the path, and so in that case, the depth would be two. Or we could say that like this starts at depth one, this starts at depth two, this starts at depth three, and so the depth is three, right? Um, kind of depends on what you care about. Like if you're thinking of this tree as as like a tree of like recursive calls or something, then the thing you care about is in fact the nodes, and so you want the depth to be 3 because that's going to be like the size of the call stack. But in general, yes, that is correct. This is a tree of depth 3. Okay, so now we can say, oh, okay, I guess I should also say like the depth of a node uh, is the length of the path from the root of that node, right? And so in that sense, I guess we could say like the depth of the tree is the maximum depth of any node. But so if we go back to here, right, we can think about like A has a depth of 1, B, C, and D each have a depth of 2, E and F each have a depth of 3, right? Does the idea of depth make sense for trees before I move on? Cool, cool, cool. Okay, so let's talk about some more vocab. Got this idea of an almost complete binary tree. Okay, an almost complete binary tree is one in which every node has either 0 or 2 children. Or sorry, um, what do I want to say? Every node except the nodes of maximal depth. Maybe this is a bad order to introduce this in. Let's back up and let's talk about strictly binary trees. Sorry. Maybe I'll leave this up, but I think this definition would make more sense if I introduced it in a different order. So, strictly binary tree is what I wrote there originally, right? So every node has either 0 or 2 children, right? So for a binary tree in general, the maximum number of children we can have is 2, right? Because there's a left child and a right child, and any one of these might be null or both of them might be null. A strictly binary tree says that in particular, we cannot have any nodes with just one child, right? So either left and right are both null, or left and right are both not null. So this is a strictly binary tree. For example, this is a strictly binary tree. This is not, because we've got this node with only one child, right? Okay. Can a regular binary tree be converted to a strict one? So there's two ways to think about this, right? I mean, first of all, yes, you can always like do a conversion. The question is like, is there a like semantically valid conversion? And maybe that depends on the semantics of your tree. But if I've got a tree like this, right, which is a binary tree, but it's not strict, I've got two options to make this a strict binary tree, right? I can take, I mean, this is the offending node, right? So um, I can either add an extra like dummy node here, and now it's strict, or I can get rid of this piece, right? And now it's strict, right? Whether one of those two makes sense depends on the application. It depends on what this tree represents, right? So if it's something like a call tree or like a recursion tree or something like that, it doesn't really make sense to add an extra call here. It doesn't really make sense to like, I mean, we could delete this node, right? But that would change the call tree. That would change what we want of the tree, or that would change what it represents. And so in that case, it wouldn't really make sense. But we'll see that like you can have a tree that represents like an array, and in those cases, you can convert it into a strict tree just by like padding out the array to a certain, or you can convert it into a complete tree, which is stronger than strict, and that just amounts to like padding the array with a bunch of zeros or something like that. Um, so the answer is sometimes. Okay. Any other questions about um about any of this so far? Cool. Keep moving on. Okay. So strict binary tree, every node has either 0 or 2 children. Um, a complete binary tree, all leaf nodes have maximum depth, right? So in particular, this tree that I've drawn here is not complete, um, because we've got, wait a minute, I think there's a, uh, never mind. Oh, yeah, never mind. Okay, that's fine. Yeah. Okay, so this tree that we've drawn here is not complete because we've got 3 leaf nodes, right? That one, that one, and that one. Um, these two have a depth of, we'll say 3. This one only has a depth of 2, right? So it's not true that all leaf nodes have the same depth, right? And so this one isn't complete. If we wanted to make it complete, or if we wanted to draw a complete binary tree, we could add in something like this, right? This is now a complete tree because now there's 4 leaf nodes, which are the 4 here at the bottom, and they each have a depth of 3, right? 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3, right? In particular, complete binary trees are completely characterized by their depth, right? If I tell you I have a complete binary tree of depth 2, there's only one possible tree. If I tell you it's of depth 5, there's only one possible tree that can look like, right? Um, of course, modulo whatever, like if we put values inside each of the nodes, then those are different. But like the shape is completely determined by the depth. Um, this means that a complete binary tree of depth D always has the same number of nodes. Um, how many nodes does a complete binary tree of depth D have? Anyone want to think about that? So if every leaf node has a depth of D, right? Or another way to think about this is like, what's if you have a binary tree and you know that it has a depth of D, what's the maximum possible number of nodes that it can have? I see 2 to the D. I see 2 to the D minus 1. 2 to the d minus 1. Yep. Yeah. 2 to the d minus 1, which equals, of course, big O of 2 to the d nodes, right? Um, and yeah, as Robert said, this is because you can sort of think about like k going from 1 to d of 2 to the k minus 1. So at a depth of k, you've got at most 2 to the k minus 1 nodes at that depth, right? Because there's one node at depth 1, that's the root. And then every node has at most 2 children. So yeah, it is. I do wish Zoom chat supported LaTeX. But yeah, so there's one node at the root, and then every node has a maximum of 2 children, and so every uh, additional depth can like double the total number of available nodes, and so you've got this formula which evaluates to 2 to the d minus 1. Okay, so actually this is sort of a good thing to keep in mind, right? Is that in general, a binary tree is going to have an exponential number of nodes, or a number of nodes that's exponential in its depth, right? And so in particular, that means that if we think about like n equals big O of 2 to the d, right? We can think about the depth of a binary tree instead as being big O of log n, right? If I've got an exponential here to solve for d, I can invert it and take like the log base 2 of n. But of course, the base of a logarithm doesn't matter for big O. And so the depth is logarithmic in the number of nodes, right? And so in particular, this means that a lot of times, if you want to do something that involves like searching through a bunch of values or like searching through a bunch of nodes or something like that, if you can somehow frame it as searching down a tree, then you convert you basically stick a log on top of whatever thing you might have, right? So if you have like n squared, or any polynomial basically becomes log of n, right? Any exponential becomes linear, and so on, which is really nice. We'll kind of see an example of this for binary search. Cool. Okay. Now maybe so we talked about strict binary trees and complete binary trees. Almost complete just means we can have leaves missing, right? So for example, the original tree that we drew was almost complete, right? This is fine because there's some leaves missing. But if I were to instead extend this out like that, this would no longer be fine, right? Because in order to make this complete, I would need to add leaves here, which is fine. But then I would need to add things here and then put leaves on them, right? And so now the stuff that's missing isn't just leaves, right? The other way to think about an almost complete binary tree is if you've got a certain number of nodes, you sort of just fill them in like top to bottom, left to right, right? So if we've got like 1, 2, 3, 4, 5, 6, 7 nodes, we fill them in like 1, 2, 3, 4, 5, 6, 7, right? So in the same way that a complete binary tree is characterized by its depth, an almost complete tree is characterized by the number of nodes it has. And the depth is still going to be like roughly logarithmic in the number of nodes, right? So this is an almost complete tree with 7 nodes. If we instead wanted an almost complete tree with just 6 nodes, we would get rid of this last one. And this is an almost complete tree with 6 nodes, right? You will notice that an almost complete tree may not be a strict binary tree, right? Because this node now only has one child, right? But that's fine. Does that make sense to people? Like strict, complete, and almost complete. So you'll notice that like complete implies strict and complete implies almost complete. But complete is stronger than both of these. So like strict and almost complete does not imply complete, right? And a counterexample is this tree right here. This is strict because this has two children, and zero children. And it's almost complete because this is like 1, 2, 3, 4, 5, right? So we've sort of filled in the nodes in the correct order, but it's not complete because we would need 2 extra nodes here for it to be complete. Okay. Does this make sense to people so far? Cool. Okay. So, um, sorry, now I'm giving kind of a whirlwind of a bunch of tree stuff. We are going to talk about trees in more detail, not this coming week, but like the week after that, the week of the first week of July, I guess. But I want to make sure that we sort of have like a introduction laid out. Um, okay. So the thing about trees, right, is as I've sort of mentioned, they're a data structure, but they don't have necessarily a semantics, right? Like a linked list is a data structure, but you can use a linked list to represent a lot of different things, right? Like you can use a linked list to represent a stack, or you can use it to represent a queue, or you can use it to represent like a window manager, right, from your programming assignment. And so what you can do with this linked list or what these different operations mean on a linked list kind of depends on what you've decided your linked list is going to represent, right? Like what's the meaning of one of the nodes of the linked list, or what does next really mean, right? What does the length of the linked list really mean? Um, and so we're going to kind of talk about some like semantic trees that you can create, or like some sort of semantics that you can assign to binary trees. And these are trees like binary trees that specifically help you with or that are specifically very useful for algorithms that we will talk about, right? Um, so the first one that I want to describe is a binary search tree. This might be kind of a review if you've seen these before, but I figure it's kind of worth going over anyways. So binary search tree. Okay. Um, all right. So as the name suggests, this is a binary tree. It is very useful for searching, right? So if you want to if you want to like determine whether a particular object is in a collection or something like that, or like find out where it is in that collection or something, um, binary search trees are great, right? So binary search tree is, I'll write it like this, right? So um, the values it holds have to be orderable, right? So like we can compare them. So like A is less than B, for example. So we could have like integers, we could have floats, we could have strings if we do like a lexical comparison. Um, but whatever data type you hold in the binary search tree needs to be something that you can something that supports like comparisons, right? Even if you define some sort of comparison operator yourself. Um, and then uh, it requires this following invariant, right? So the invariant is that if I've got like a parent node with a left child and a right child, we'll say L dot value is less than, we can say less than or equal to parent dot value. And then parent dot value was less than or equal to R dot value. Right? So it sort of enforces this like this sort almost, right? So the parent is always going to be between its left and right children in terms of value, right? So if it's like an integer, this could be 3, this could be 1, this could be 4, and that would be fine. If this was 5, that would no longer be fine because the parent isn't smaller than its right child, right? Um, we can use this for a very efficient search, right? Uh, so if I've got like a tree, if I've built a binary tree, right? We'll talk more in detail about like building binary trees, and there's like a bunch of choices you can make, and like certain things are better than others. But for now, if we assume that we've got a binary tree and we want to find some particular key, like we want to see if some particular value is contained, right? So maybe we can write pseudocode for this, like contains, right? And we've got a tree, and we've got a value, right? Um, so if first of all, if I found a value, right? If tree dot val equals value, then return true. I found it. And now the thing is, if I had an array, I would basically have to loop over every possible value, right? I'd have to like loop through, I'd have an O of n for loop that just looks at every value in the array and tries to determine whether it's the one that I care about. And if it is, then I return it. Otherwise, I don't. Um, but now that I have a tree, I can decide whether I want to go on the left side or the right side, right? So I can say if tree.val is less than value, that means value is greater than the thing we care about. And so I'm going to recurse on, anyone want to tell me the left or the right in this case? On the left? Okay, so let's think about this, right? If I've got a tree, um, and this has a value of 3, right? This is a proper binary tree. If the thing that I'm looking for is, let's say, like 5, right? And I go here, I see that uh, tree.value, which is 3, is less than 5, right? Is 5 going to be on the left side or on the right side? If this value exists, it's going to be on the right, exactly. So we're going to recurse contains tree.right on the value, right? Otherwise, we're going to recurse on the left. Yeah, it's weird because the less than is sort of flipped from the way you want to think about it. Um, but yeah, and we sort of had this as an example in the master theorem lecture, I think. But if we look at like what the complexity of this looks like, you get something like T of n equals T of n over 2 plus theta of 1. And so this is theta of log n, right? Um, and the way to think about what's going on here is at every step, we're sort of we're like cutting off half of the values at a time, right? Oh, was that a hand? That's cool. I didn't know that was a thing. Is there a question? All right. Um, Okay, so that's binary trees, right? So yeah, at every step of a binary search, because it's framed as a tree, we can check just one of the two children, and so we're sort of like having the size of the space that we have to check. And so that gives us a logarithmic complexity, assuming that our data is somehow um, like orderable, sortable, and that it's already put into a tree, right? So obviously building the tree is going to take some time, but if we have a tree, then we can search it efficiently. Okay. The other kind of tree that I want to look at is a heap. This one is in particular important, so I want to make sure I cover it before the end of class today because we're going to talk about it, or I'm going to talk about it in the recorded lectures. Um, so a heap, uh, there's two kinds of heaps. This is again for like sortable data. Um, you can say like max heap or min heap. And the idea here is the parent value. We'll say it for max heap. The parent value is greater than both children, right? So an example of a valid max heap would be something like if 5 is the parent, and then we've got like 3 and 4, and then like 1 and 2, and then like 2 and 3, right? This is a max heap because every parent is greater than its children. If I were to like swap the if I were to swap these and put the 2 here and the 5 here, this would no longer be a max heap because like there's two issues here, right? So there's this edge where the child is bigger than the parent, and then there's this edge where the child is bigger than the parent. So there'd be two things to fix, right? Thinking about it this way is kind of important because later we will talk about this procedure called heapify, right? Which takes an arbitrary tree like this and it sort of canonically turns it into a max heap, right? Or a min heap, right? So if instead of a max heap we talk about a min heap, then we say the parent value has to be less than both children, right? It's the same thing, just flip all the signs around or flip like yeah, flip the signs around. And so we can talk about like max heapify or min heapify. Um, but yeah, so this will end up being very useful. This is a good way to implement something called heap sort. So the idea is going to be we're going to throw things into a heap, and then we're going to heapify. And because of the semantics of a heap, the parent has to be greater than both of its children, which means that the maximum element in the heap is going to be at the root. And so we just take that, and that's our maximum element, and then we heapify the rest, and we get the new maximum, and then we heapify the rest and get the new maximum, and so on, right? So, and then to, I don't know, maybe like spoil the surprise a little bit, heapify ends up being something like O of log n if you do it right. And so heap sort is like for every single element you heapify and then you grab that element, and so you get like an O of n log n sorting algorithm, right? Uh, if that doesn't track yet, if you don't have any intuition for that yet, that's fine. I'm going to talk more about it in the recorded lectures, but that's sort of the idea, right, of a heap. Um, okay, I really want to talk about like KD trees and quad trees because those will be useful for the next project. But I think before I do that, I need to talk about representing trees with arrays, right? So we sort of had this thing where like linked lists are a flexible version of arrays, right? Like we have an array, and the array has like implicit next pointers, right? Like this one implicitly points to here, right? If we think of an array as a linked list somehow, right? Or if we think of like encoding a linked list as an array, we've got these implicit next pointers, right? And there's Uh, this is good in some sense, right? Like packing things as an array is nice because we can just allocate memory once. We get really nice cache behavior, right? As soon as we load one thing, like probably this entire block gets loaded into the cache, and so all of our accesses are really fast. Um, and just in general, like arrays are fast to work with, right? Um, but the problem is we sort of lose out on this flexibility, right? Like we can't insert into the middle anymore. We can't really resize it anymore without copying everything over and like reallocating and stuff like that. But if you have a fixed size known ahead of time, then there's no reason not to use an array. This is sort of review from the linked list stuff. But the thing that I want to point out is that binary trees have a version of this as well, right? So you can take an array and think of it as a binary tree by having the first element of the array be the root node, and then its children go into the next two elements, and then the left child's children go into the next two elements, and the right child's children go into the next two elements, and then this guy's children go into the next two elements, and so on, right? Until you run out of space in the array, or until you run out of nodes in the binary tree, right? So, for example, um, if we've got a tree like this, and this works without any assumptions on the tree, right? Our tree might be it might be complete, it might not be complete, it might be strict, it might not be strict, it's whatever, right? 1, 2, 3, 4, 5, 6. Okay, so this has 6 nodes. Someone shout out 6 numbers. Just like give me 6 numbers. 3. Okay. See a 3. I need 5 more numbers. 7. Hell yeah. All right. 8, 5, 9, 56. All right, cool. Okay. Yeah. So the way we can turn this into an array is, like I said, we put the root node. Have you been obsessed with 56 this whole week? Uh, that's a good question. So we put 3 here, right? Its left and right children go next to it, so 7 and 8. And then we look at 7's left child, which is 5. We look at 7's right child, which is null, so we leave this blank. Then we look at 8's children, which is 9 and 56, right? This has the nice property that, like, if you think about the parent goes in index 0, its children go in 1 and 2. 1's children go in 3 and 4. 8's children go in 5 and 6, right? And so in general, if you pack a tree into an array, then the left child of node n is going to be 2n, right? Maybe 2n plus 1. Yeah, because we're 1 indexing. And then the right child, I said, what am I doing? The right child is going to be 2n plus 1, right? If you pretend that this is 1 indexed, I guess. Know what I want to say? Yeah. Is that what I want to say? No, I think it's just, what do I want to say? Well, this is the idea, right? Maybe if I start this at 1, 2, 3. Yeah. Okay. I'm not gonna 0 index this. I'm gonna 1 index it. And then I'm gonna get rid of the ones here. So the left child is at 2n, the right child is at 2n plus 1, right? In particular, this also means that you can very easily find the parent, right? So like for a linked list, unless it's like a doubly linked list, we don't have like a previous pointer, right? But for here, if I know the index of a node, I can find its parent just by dividing by 2 and then rounding down, right? So if it was a left child, then it's going to be even. It's going to be an even index, and I'm just going to divide by 2 to get to its parent. If it's a right child, it's going to be odd, so I'm going to divide by 2 and then like round down, like cancel out, sort of floor out the 0.5, and then I can get to its parent, right? So in particular, this is also just a way of like looking at an array and treating it as a binary tree, right? So without doing a bunch of allocations, without writing a bunch of pointers and stuff like that, if you just have an array, you can pretend it's a binary tree by pretending that the first element of the array is the root, and then pretending that the left and the right children of each element are the ones that index 2n and 2n plus 1. And again, foreshadowing, this comes up in heap sort, right? We start with an array that we want to sort. We think of it as a binary tree, then we heapify it, and then uh, read off the top one at a time. I don't know why I'm spoiling everything here, but does that make sense? It's intuitive. Cool. I'm glad. The last thing that I'm going to talk about in like the 2 minutes that we have left are KD trees because I think they're so incredibly cool. Um, so the setup for KD trees is this is no longer uh, like sortable, right? This is not working with numbers anymore or arrays anymore. It's working with spatial data. So if you imagine that we have like a plane, right, with a bunch of points. Okay. Um, I can think of like I've got a plane with a bunch of points, and I want to somehow like I want to search points, but I want to do it in a way where I care about how close two things are, right? So you can imagine if this is like a game, right? Shadow of oh yes, Elden Ring, great. Yeah, so you can imagine that this is like a game, and these are like hitboxes or something like that, and you want to see if like a if something intersects, right? Uh, and so maybe you've got like some object over here, right? And you want to see which, if any, of these points, which, if any, of these like hitboxes it hits, right? Now, visually, we can look at this and we can say, okay, yeah, we really only need to check here. But if you've just got this like list of points stored as a list, then you have to loop over everything, right? So the idea of a KD tree, and again, I will talk about this in excruciating detail during a later lecture. But the idea of a KD tree is we take this list of points and we split it down the middle, right? And so now we've got a left half and a right half. And I take one of these halves and I split it down the middle. And then I take this half and I split it down the middle, right? I can sort of choose where to put these splits, right? But I can do something like this, right? I can just keep splitting until I've hit some condition, right? Maybe I want to keep splitting until I've got only one node in every piece, or maybe I want to like split out to a certain depth or something like that. But now I've got all of my points stored in a tree instead of a list, right? And so now when I'm looking at like when I want to see if this point collides with anything, right? I just look at its coordinates and I decide, okay, does this go in the left half or the right half? It goes in the left half. Does it go at the top or the bottom? It goes in the top. Does it go on the left or the right? It goes on the left. Top or bottom? It goes in the top. And so I can like do this like logarithmic search to sort of figure out which box this thing lies in, and then I only have to search all of the points within that box, right? So I can kind of like uh, I can narrow down on the thing that I care about. So this is the KD tree. Um, the D stands for the dimensionality, right? So this is two-dimensional. You can do this in like n dimensions, right? You could imagine instead of you could do this in like 3 dimensions, and instead of lines, you're like slicing planes or something like that. Um, there's a version of this called a quad tree, which does something similar, but it's like specific for 2 dimensions. Um, I figured I'd throw that out there. It's 941. Um, So that's how an Excel tree map works. The thing is, I don't know anything about Excel. Like anytime I need to use Excel, I use Python instead. So if you say that's how it works, I am going to believe you. Um, yeah. Oh, sorry. Yes, attendance poll. When can a uh, binary search tree and heap, are these mutually exclusive? If so, why are they mutually exclusive? If not, what does it mean for a tree to be both a binary tree and a heap? That's the poll. That's the attendance poll. I'll create a thing for it on Brightspace. Um, cool. Oh, there's Python and Excel now. Oh yeah. So maybe I'll just write this down. Um, hmm, when is a tree both a binary search tree and a heap? That's the poll. There's a text option. Oh my God. Look at that. I'm learning new things. This is great. Anyway, that's the okay, maybe maybe that was a subtle way of telling me to fix my handwriting. Um, why do I have caps lock on? When is a tree both a binary search tree and a heap? Is this possible? There we go. That's the attendance poll. And that's all I got. So, uh, thanks for showing up, everyone. Have a good weekend. Be on the lookout for I will post the video and the like the recording from today, and the pre-recorded lectures and the the assignment, the problem set. Thank you. I will do my best to have a good conference. I will see you all in 2 weeks.